We all think we know gravity. It's the force that pulls an apple to the ground, the force that keeps the Earth orbiting the sun. But today, we're going to dive into an idea that flips all of that on its head, a theory that suggests we've had gravity completely backward this whole time.
So just let that sink in for a second. What if the force holding you to your chair right now isn't the Earth pulling you down, but the entire universe pushing you down? It's a wild idea, and it challenges some of our most basic assumptions about how reality works.
To really wrap our heads around this, we need to take a quick trip back in time, to the very beginning of our modern understanding of gravity. Because right at the heart of it, there's always been a massive unanswered question.
Right, so here's the thing about Sir Isaac Newton. The guy was an absolute genius, no question. His laws of gravity, they worked perfectly. You could use them to predict the orbits of planets with incredible precision. He completely nailed the how of gravity. But when anyone asked him why it worked or what it was, he basically said, "I have no idea." He left this giant gaping hole where the actual cause of gravity should be.
And believe it or not, for hundreds of years, that's pretty much where science left it. Gravity was just this mysterious, invisible force that somehow reached across the emptiness of space and worked. They called it action at a distance. But, that's not really an explanation, is it? It's just a label for a mystery. And a mystery that big is just begging for someone to try and solve it.
And that's exactly what happened. Back in the 18th century, a new idea surfaced, one that was simple, mechanical, and totally different from the spooky action at a distance everyone was used to. This is where a physicist named Georges Louis Lesage steps into the story. He looked at what Newton had done and thought, okay, describing the effect is great, but what's the engine under the hood? What's actually causing this force? He wanted to get to the nuts and bolts of it all.
And Lesage's idea was just beautiful in its simplicity. Imagine that all of space is filled with these tiny, super-fast particles, flying around in every possible direction, like a constant cosmic hailstorm. Now, if you're out there all by yourself, you're getting hit equally from all sides, so you don't move. But what happens if another object, say the Earth, is near you? Well, now the Earth is blocking the particles that would have hit you from below. That means you're getting hit by more particles from above than from below. And the result? You get pushed toward the Earth. That, Lesage said, is gravity. It's not a pull, it's a push.
It's so elegant, so intuitive, right? It feels like it should be the answer. But, and there's always a but in science, when other physicists started to really poke at the idea, it started to run into some serious trouble. This brilliant idea had a few fatal flaws.
Here were the three big deal breakers. First, the heating problem. If we're constantly being bombarded by these high-speed particles, all that energy has to go somewhere. We and everything else should be glowing white-hot, but we're not. Second, the drag problem. If the Earth is moving through this storm of particles, it should be like walking into a strong headwind. It should slow down over time, right? But it doesn't. And third, the shielding problem. If the moon can block these particles, then during a solar eclipse, it should cast a gravity shadow, and we should feel slightly less pull from the sun. But experiments show that doesn't happen at all.
With the physics they had at the time, these problems were just impossible to solve. There were no good answers. So, Lesage's theory of pushed gravity, as cool as it was, got thrown onto the scrap heap of scientific history. Science moved on, Einstein came along with his theory of general relativity, and this simple, mechanical idea was all but forgotten. But what if those fatal flaws weren't so fatal after all? What if they just needed a little 21st century physics to solve them? This is where the story gets really good. This is the comeback of pushed gravity in a new, modern form, Graviton Pressure Theory, or GPT. All right, let's tackle those old problems one by one, starting with that big one, the heating problem. The original theory said we should all be cooked to a crisp from the constant bombardment of particles. So how does the modern version fix that? Well, GPT reimagines the whole interaction. It says this isn't a random hailstorm, it's a field, and objects interact with it based on phase coherence, basically resonance. The best analogy is a radio. You're surrounded by hundreds of radio signals right now, but your radio only plays the one station it's tuned to. In the same way, matter is only tuned into a very specific, tiny slice of this graviton field. No more random bombardment, and poof, no more heating problem. Okay, on to problem number 2, the drag. Why isn't the Earth slowing down as it plows through this field? Where's the cosmic friction? GPT's solution here is just fascinating.
It suggests that as an object moves, it creates something called a coherence corridor in the field. Think of it like a boat creating a wake in water, only this wake actually makes it easier for the boat to keep going. The field itself sort of adapts and remembers the object's path, effectively getting out of the way, so the drag just disappears.
And that brings us to the third and final hurdle, the shielding problem. Remember, the moon should cast a gravity shadow during an eclipse, but it doesn't. Why not?
The answer, according to GPT, is that it's not about physical blocking at all. The field doesn't interact with an object's shape or what it's made of. It interacts with its total mass energy configuration, which creates a unique coherence pattern. And this is so cool because it perfectly explains why a feather and a bowling ball fall at the same rate in a vacuum, the famous equivalence principle. It all just clicks together.
So, if this updated theory can actually solve all those old problems, what does that actually mean for us? Why does this matter? Well, the implications here go way, way beyond just gravity.
Let's just compare them side by side. Newton described what gravity does. Einstein gave us this incredible geometric picture of warped spacetime. But neither of them offered a direct physical cause. GPT does. It says gravity is a real pressure. And notice that last row. It even proposes a physical mechanism for inertia. That is a huge deal. The question of why things resist changes in motion has stumped physicists for centuries, and this theory offers a tangible answer. And this is where it gets really mind-bending. In this worldview, fundamental concepts we take for granted like inertia or momentum aren't actually in the objects themselves. They are properties that emerge from how matter interacts with this universal field. Inertia is just the field's memory of an object's motion. Momentum is the persistent corridor it's carved. Even time dilation, how time slows down near a massive object, is explained as the intense pressure from the field slowing down matter's internal refresh cycle. It's a whole new way of looking at reality.
So, what does this all mean for the future? Now, GPT isn't necessarily the final answer to everything, but what it does, and what's so exciting, is that it reopens a door to a whole new way of thinking that was shut for more than 200 years. And I think that's such a powerful lesson about how science really works. We like to think of progress as a straight line, always moving forward, but it's not. Sometimes the most exciting path forward is to go back, find a forgotten idea, and look at it again with fresh eyes and all our modern tools. And that brings us right back to our original question. This theory, born in the 18th century and reborn today, forces us to ask, is the universe pulling us in, or is it pushing us together? The answer could really change everything we think we know.